All right, Chemistry 3111. This is the last part of Chapter 14. So the chapter that deals with infrared spectroscopy, which is where we identify functional groups in an organic compound, and mass spectrometry, which is where we attempt to determine the molecular formula of a compound, or at least get some good information about fragments in a compound. Now, what can you do with a molecular formula? Right? You might think, well, I just have a molecular formula. There's not much that I can do with that. But there's actually quite a bit of information that can be gleaned from a molecular formula that we oftentimes, again, determine using mass spec. Something that you might have noticed is that saturated hydrocarbons follow this generic formula here, CnH2n plus 2. Let's say I have ethane, right? You have C2H6, so that follows 2n plus 2, right? If you take C is 2, right? And then you have H2 times N, which is the same number 2 plus 2. So 2 times 2 is 4 plus 2, and that gives you C2H6. I mean, you could do that for any hydrocarbon, even if you had octane, 1, 2, 3, 4, 5, 6, 7, 8, right? It has the formula C8H what? 2 times 8 is 16 plus 2 would be 18. And so all saturated hydrocarbons are going to have that generic formula there, CnH2n plus 2, and you need to know that, okay? But what about compounds that have pi bonds and rings? Well, we call having a pi bond or a ring in your molecule, we call that a unit or a degree of unsaturation. So again, a pi bond or a ring. And for every degree of unsaturation in an organic compound, the number of hydrogens gets reduced by 2. So if you look over here on the far left, we have pentane, right? This is pentane, and you can see that the formula is CnH2n plus 2. But if you look at this molecule here, this is called 1-pentene, and we'll look at alkene nomenclature later on in the class. But what do we have here? We have one pi bond in the molecule. Remember, any bond after a sigma bond is a pi bond. So if we have one pi bond, that should reduce the number of hydrogens in the molecule by 2. If you take 12, you subtract 2, you get 10. There you go. So the alkene, pentene, or 1-pentene, has this formula here. Now, the generic formula would be CnH2n. All I have to do is multiply the number of carbons by 2, and that tells me the number of hydrogens in my alkene. Now, what if I had an alkyne? How many pi bonds are in an alkyne? Well, the answer is there's 1, 2, right? 2 pi bonds in an alkyne. So each one is going to reduce the number of hydrogens in the molecule by 2. 2 times 2 is 4. So instead of having 12 hydrogens total, we'll have 12 minus 4, which is 8, right? And so the generic formula here for an alkyne would be CnH2n minus 2. So we have an alkane, then we have an alkene here, and here we have an alkyne, okay? Now, these formulas here, okay, all three of these, or these two formulas here, they don't necessarily represent always an alkene. They don't necessarily always represent an alkyne. The formula CnH2n represents one unit of unsaturation, which represents a pi bond or a ring, okay? And the formula CnH2n minus 2 doesn't necessarily represent an alkyne. It represents 2 degrees of unsaturation. Well, what other kinds of scenarios could we have where we would have, let's say, 2 degrees of unsaturation? Well, let's take a look here. So if you take a look at the isomers with this molecular formula, C4H6, what's the generic formula here? It's CnH2n minus 2, right? You just did that by mental math. If you multiply 2 times 4, you get 8, you subtract 2, which gives you 6. So this tells us that this compound, or maybe I should circle this one, this compound here has an HDI, or a hydrogen, what we call a hydrogen deficiency index, equal to 2. Okay, it says here that 1 degree of unsaturation, we call that a 1 unit on the hydrogen deficiency index. So sometimes in this class, you'll hear me talk about an HDI, and then other times you'll hear me talk about a U, and that's when I'm getting lazy and I just want to call it the number of units of unsaturation, right? It's a little bit faster, but they both mean the exact same thing. So again, what kind of scenarios could we have 2 units of unsaturation? Well, we could have 2 double bonds, right? You see that in these molecules here, we have 2 double bonds. We have a double bond here, another one here, and you see that you have 2 double bonds on the same carbon here, which is kind of interesting. We don't really talk about that a ton in this class. The next one is a triple bond. Why would a triple bond fit the bill? Because a triple bond has 2 pi bonds, right? There's 2 pi bonds here and 2 pi bonds there. What about if we had 2 rings? Remember, each ring equals 1 unit of unsaturation, or 1 unit on the hydrogen deficiency index. And since we have a ring here and we have a ring here, there you go, that fits the bill. And if you don't believe me, if you're like, I'm a little bit unsure about that, what you could do is just redraw the whole compound out, and you could draw all the hydrogens in if that helps you. We have 2 here, we have 2 here, and we have 1 here, and we have 1 here. So we have a total of 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6 hydrogens. Trust me, it's going to work every time. And then the last scenario that we could have would be 1 ring and 1 double bond. And you see there's 4 different examples here. Now you might be saying, well, jeepers, Mr. Dion, if you give me a formula that doesn't tell me a whole lot if I have 1, 2, 3, 4, 5, 6, 7, 8, 9 different possibilities. Well, the thing is that when you're solving problems in this class that deal with spectrometry and spectroscopy, oftentimes I'm not going to give you just a molecular formula. I'll give you a molecular formula and an infrared spectrum, right? So right away, you'd be able to tell, let's say you had a terminal alkyne, right? An alkyne with a carbon-hydrogen bond. Let's say that was the compound and I gave you an IR. Well, you would see the characteristic carbon-hydrogen stretch from an sp hybridized carbon at 3300. You would see the triple bond between 2100 and 2150, for example. So we use everything that we have at our disposal. Okay, so any problem that I ask you in this class, you're always going to have enough information to solve the problem. Sometimes I'll give you just an MS, sometimes I'll give you just an IR, sometimes I'll give you both. Okay, depends on the situation, but we always provide enough information for you to solve any problem. All right, let's move on from there. You might be wondering, well, that's all well and good for molecules that only contain carbon and hydrogen, but in organic chemistry, I see a lot of oxygen, I see halogens, I see nitrogens. What about those? Okay, how are those atoms going to affect the hydrogen deficiency index? Well, there's 3 kind of rules that we're going to look at. The first one is for halogens, the next one's for oxygen, and then the last one is for nitrogen. I can cover these pretty quickly. The first one is that if we have a halogen in a molecule, you treat it as just the same as if it was a hydrogen, right? Because all the halogens in this class will only ever have 1 bond, right? That goes all the way back to chapter 1 when we talked about Lewis structures and molecular geometry. I know that you have polyvalent halogens in general chemistry, not fluorine, of course, but in this class, you'll never see that. Okay, so since halogens will only ever have 1 bond, you can treat them just like they're a hydrogen atom. So if we have C2H5Cl, you can treat it the exact same as if it was C2H6. What's the generic formula? It's CnH2n plus 2. And therefore, you know that there's no units of unsaturation in this molecule, right, in chloroethane. What about an oxygen? Good news. An oxygen doesn't change anything, okay? You just ignore it. Pretend it wasn't even there. So if we have C2H6O, which is what we have here for ethanol, you can treat it just like it's C2H6. The oxygen doesn't do anything. And so the same thing here, you'd have the formula CnH2n plus 2. And so there's no units of unsaturation in ethanol. Good enough. All right, nitrogen gets a little bit more interesting. I'll erase my scribbles here. Anyhow, it says here that for the HDI scale, when you have a nitrogen, it increases the number of hydrogen atoms by 1. So if we look at the formula of ethylamine that's over here, we have C2H1, 2, 3, 4, 5, 6, 7, H7N. And so we increase the number, the nitrogen increases the number of expected hydrogens by 1. And so you remove a hydrogen, okay? So you could treat it as if it was C2H6, right? Again, let me rephrase that because I don't think I said it right the first time. Is that the nitrogen increases the number of expected hydrogen atoms by 1. So you have to lose 1, okay? And you see that this formula is, again, CnH2n plus 2. Now, if you're like, oh, how am I going to put all that stuff together? If I have a molecule that's got carbon and nitrogen and oxygen and hydrogen, right? And chlorine and maybe a fluorine in there. Well, the good news is that you can just use this formula here. I will not provide this formula for your quiz. You need to have this formula memorized in this class. Okay, so memorize this formula. You might be thinking, oh no, not another thing to memorize. Well, the good news is that it won't be for naught. Okay, I promise you it won't be for nothing. That you're going to use this formula countless times throughout this class, so much so that after you've memorized it for this quiz and we start using it, especially once we get into chapters 7 and 8 and 9 and stuff like that, it will become second nature. You won't even have to think about it. Like when I calculate HDIs or U's, whatever you want to call them, I don't even think about the formula, right? I just kind of solve it anyhow. And you will do the exact same thing as me, I promise. Okay? So there's our formula, and I wouldn't expect you to have that memorized in 10 seconds. So let's write down the formula. So for HDI, which is the same thing as a U, units of unsaturation, we have 1/2 times 2 times the number of carbons plus 2 plus nitrogens, the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens, right? X represents a halogen, and then that's it. And that tells us our HDI. So if we try it for A, we start with A, we have 1/2 times 2 times 6 plus 2. There's no nitrogens. There's 10 hydrogens, and there's no halogens. So if we do all that up, we get 2 times 6, which is 12, plus 2, which is 14. 14 subtract 10 is 4. 4 multiplied by 1/2 is 2. And so the HDI for this compound right here is going to be equal to 2. I'd like you to give a try for B and C and D and E, see how many you can do. Okay, take a second and try them. And once you're done with those, you could give this one a try here. I made my own here, so C17, H19. And if you need a calculator, you can use a calculator. And same thing in the quiz, if you need a calculator, go ahead and use one. So if anybody has an answer for B, if you could throw it up here in the chat, that would be great. Well, let's try B. Okay, let's give it a shot here. So let's see. For B, we've got HDI is equal to 1/2 times 2 times 5 plus 2. There's no nitrogens. There's 10 hydrogens, and there's no halogens. So 2 times 5 is 10 plus 2 is 12. Subtract 10 is 2. 2 multiplied by 1/2 gives me an HDI equal to 1. Okay, is that more clear? I'm not sure how people got 0 from that one. I'm unsure about that. I mean, another way to look at it is you remember that oxygen has no effect, and you see the relationship between these two numbers. It's CN and H2N. Does that clear it up? I'm not sure how people get 0. Anyhow, let's try another one. Let's try C as a group. I'll give you a second. See if anybody can spit the answer out for C. All right, so I see a few people have put the correct answer. So for C, we do HDI is equal to 1/2 times 2 times the number of carbons, which is 5, plus 2, plus how many nitrogens? We have 1 nitrogen, subtract 9 hydrogens, and we have no halogens. So we have 2 times 5 plus 2, that's 12, plus 1 is 13. 13 minus 9 is 4, and we multiply that by 1/2, and we get 2, like that. So just a little quick mental math there. Okay, let's try one more. Let's try D. Give that the old college try. D. Give you a second. Yeah, I think you guys are on the right track now. So if we look at D, get my pen here. We have HDI is equal to 1/2 times 2 times. We have 3 carbons plus 2. There's no nitrogens. We have 5 hydrogens, and we have 1 halogen. So that means my HDI is going to be 2 times 3, which is 6, plus 2, which is 8. 8 subtract 6 gives me 2. 2 times 1/2 is equal to 1. And so my HDI would be 1 for that one. Okay, good. Well, you could try the next one. You could probably do it in your head pretty quickly because you see the relationship is CnH2n. So that means that you would have an HDI equal to 1 for this one. And if you want to give this monster here a try, you give that the old college try. I'll just tell you the answer for this one is 9. Okay, so it's a pretty big molecule with lots of different units of unsaturation in it. Okay, anyhow, there we go. So that basically covers the rest of the chapter. That's it, people. So we've covered everything. And again, we can always use the HDI to determine the number of units of unsaturation, right? And then we would use that in conjunction with something like an infrared spectrum or something of that ilk to help us determine, to help us determine the identity of our compound. Well, with that in mind, just give me one second here, and I want to take a look at a problem with you, which is this one here. I wanted to skip all the way to a problem that kind of relates to what we're looking at right now, and that's this one right here. So question number 12. It says deduce the structure of the following compound. So notice that we've been given a beautiful infrared spectrum. Okay, we have a nice IR spectrum, and then we have a molecular formula here. So if this is our molecular formula, I wonder if anybody could tell me the number of units of unsaturation, the HDI, the hydrogen deficiency index, in this molecule. Yeah, I think Moira, or Maya, sorry, I think you're in the right vein. That it's 2, correct? Right? Again, you don't have to, or you can memorize the formula, which I recommend doing, I guess, at the beginning. Anyhow, you have 1/2 times 2 times the number of carbons, which is 3, okay, plus 2. There's no nitrogens. We have 3 hydrogens and 1 halogen. So look, we'd have 2 times 3, which is 6, plus 2, which is 8. 8 minus 4 gives me 4. 4 times 1/2 equals 2. So what are my possibilities when I have 2 units of unsaturation? I can have 2 pi bonds. I could have a triple bond. I could have a pi bond and a ring, right? I can have 2 rings, as we saw a few slides ago. So now what we're going to do is, now that we know that we've got 2 units of unsaturation in this molecule, let's try to figure out what type of units of unsaturation we have. Now you notice that the scale of this infrared spectrum is a little different than some of the ones that you might have seen before. But if we draw a line at 1500 reciprocal centimeters, we draw a line right here. So this is the fingerprint region down here. Let's get into the diagnostic region, which is above 1500. And I'm also going to draw a line at 3000. So if we have 2800, 2900, 3000 is right there. There we go. So this would be 3000 reciprocal centimeters. So this is 3000. And this is 1500. So does anybody see anything in here that piques their interest, that tells them, I think I see some interesting signals here? Anybody? Let me maybe draw your attention. Do you see anything above 3000? Are there any signals above 3000? The answer is
How about
yeah.
the peak at 5,000 for the double bond?
Sorry, can you repeat that?
Like there's like a little peak at 24,000. Will that be like a double bond?
So 2400, you mean this peak here? Because this is 2400 right here.
Yeah, that one. Sorry.
No, that one's, I would say that one is really too small to be able to figure out what that might be. So I would draw your attention to above above the 3,000 mark, right? It goes, so look carefully at the scale. Watch, if I blow it up here. Look, this is 3,000, this is 31, this is 32, this is 33. So this is 3,300 reciprocal centimeters. Now, what kind of peaks do we see that are sharp that are at 3,300 reciprocal centimeters? This is probably sp hybridized carbon-hydrogen stretch, right? And where would we find that? We would find that in an alkyne. And since we have 2 units of unsaturation, now we can say this is probably an alkyne. What else do we see from an alkyne? If you go over to your sheet that talks about all the different IR absorbances, and again, you're going to have that sheet with you during your quiz, you'll see that we also have the carbon-carbon triple bond stretch between 2150 and 2100 reciprocal centimeters. So look, the scale goes like this. It goes 2000, 21, so this is 2100, and then this is 2200 here. So it looks to me like it's around 2150, right? This is around 2150 reciprocal centimeters, and so this is the carbon-carbon triple bond, okay? So now that we've identified that this compound is an alkyne, and it has a carbon-hydrogen, an sp hybridized carbon-hydrogen bond, we know that we have this in the molecule. Okay? We know that we have a carbon-carbon triple bond, and we know that we have a hydrogen attached over here. Well, if there's only 3 carbons in the molecule, there aren't many possibilities, right? We have a carbon here, we have a carbon here, and we've got 1 more carbon, and it's going to have to be attached over here. Now, what have we got left over? We used up all 3 carbons. We used up 1 of the hydrogens. So what have we got left? We've got 2 hydrogens and a chlorine. Well, carbon always has to have 4 bonds. So if we draw 1, 2, 3, like this, because we've already got the 4th bond over here, we're going to put the 2 hydrogens and the chlorine. And so there you go. We've solved the structure of the compound, right? All it is this. We've got a triple bond, and we've got a chlorine. There's the bond line structure of the compound. Give me a thumbs up if that makes some sense to you. There's a rationale to it. Okay, remember, I'm not going to give you some kind of problem that's impossible to solve, that you've got to be digging around for signals that are super small, okay? Sometimes in organic chemistry, we see signals that are small, that are important. But generally speaking, if you see something with this kind of absorbance, you don't want to ignore that, right? That's humongous, okay? And again, it's in the diagnostic region. Well, with that in mind, let's try another one that's in the same vein. It says here, deduce a structure for the following compound. We have a molecular formula, which is C7H8O. I'll throw this out here to my students first. Can anybody tell me what the HDI is for this compound? Take your time, make sure you get it right. Yeah, thanks, Kayla. Absolutely. Yeah, everybody, almost everybody is right. Right, so it's 4. We have an HDI of 4. Okay, I'm not going to go over the math again, but we have an HDI of 4 here. Now, if we have an HDI of 4, what kind of possibilities do we have? We've got 4 double bonds, right? We've got a ring and 3 double bonds. We've got 2 triple bonds, right? I could keep going on. But if I draw a line at 1500, so 1500 is here. Need a ruler, right? For my iPad. So if I draw a line at 1500, right there, and I draw a line at 3000, 3000 would be right around here. Before we really get into the nitty-gritty here of trying to decipher what kind of compound this is I'm just going to throw it out there to my students. Is there anything that you guys notice in the infrared spectrum that you're just, yeah, I think I see something in here that might be of interest, maybe a functional group that we've seen a few times? Yeah, exactly. Thanks, Megan. Thanks, Lauren. Yeah, absolutely. You're all right. It's an alcohol. Absolutely. Every single one of you. See, now you're getting used to it, right? You see that here we have an oxygen hydrogen stretch. right? So we know that we've got an alcohol. Now, I like to write down everything that I know. So I know that somewhere in the molecule, I've got this, right? I've got an alcohol. Now, obviously, I've got a lot more to go, but I've got an alcohol in there, okay? Now, I am going to throw this out there to you. This might not be simple, okay? Um, but does anybody have an inkling where these 4 units of unsaturation might come from? Once I tell you, it'll be pretty abundantly clear, but does anybody have an idea where you get the 4 units of unsaturation from? Nope. Okay. Well, when you have 4 units of unsaturation or more in this class, where I like to go is if you look at your sheet and you look down, it says alkane, alkene, alkyne, what's next? Aromatic. So what it tells you is that at 1600, you have carbon-carbon double bond ring stretching, right? Because with an HDIF4, if you have an aromatic ring, you've got a ring and 3 double bonds. So that would cover all of it. So here's the answer, you guys. Normally, an aromatic ring will have 2 to 3 signals between 1475. So this is the 1600. So for aromatic, let's write it down here. Aromatic will usually have between 1600 to, come on, 1475 reciprocal centimeters, okay? And you'll have 2 to 3 absorbances or signals, okay? So if you look right here, and I'll maybe use the highlighter, okay? Right in this range right here, you see that we have a big old absorbance here and another one here, and there's one like tailing here. And again, it's usually 2 to 3 absorbances in the 1600 to 1475 reciprocal centimeter region. And so this represents a carbon-carbon double bond stretch, but you can just put carbon-carbon double bond, but then be sure to write aromatic, right? Because if you have a carbon-carbon double bond in an alkene, right, that's going to come up around 1630. So if this is 1700, 1630 is around here, and there's nothing here. Okay, so this is very clearly an aromatic compound. So that means that we've got this, right? We've got an aromatic ring that covers 6 of the carbons. We've got to have the hydroxyl, the OH, so that covers the oxygen, and it covers 1 of the hydrogens. So that means I've got 1 carbon left over and 7 hydrogens. Well, let's think about this very carefully. Okay, now this is kind of like solving a puzzle, right? Are there any other, functionalities in here that you could say, well, this is probably something? I mean, you could go to the alcohol, right, and look for the carbon-oxygen stretch between 1,000 and 1250. So that might be, one of these here is probably the carbon-oxygen stretch. Okay, we'll just circle a bunch of them here, but it's probably one of these. Okay, actually, I'd say maybe it's probably the one that's the sharpest here, the strongest one. Anyhow, but still, that doesn't get me any further. Okay, so it's kind of like solving a puzzle. Well, one thing that I notice in this spectrum is that if you look below 3,000, just below 3,000, and a student in our class asked me this on Wednesday. The student said, why are there always peaks or absorbances at, just below 3,000, 3,000, 2,900, right? Why is that so common in our infrared spectra? Because those represent sp3 hybridized carbon-hydrogen bonds, which normally we don't label, right? Normally I wouldn't point those out. But here, if you just look at an aromatic ring, every carbon in an aromatic ring is sp2 hybridized. But based off of this IR, we know that we've got a carbon that is sp3 hybridized. Well, hold on. If I've got 1 carbon left over, the only way for that carbon to be sp3 hybridized would be for it to be a methyl group, right? That's the only possibility that for having 1 carbon and having it being sp3 hybridized. So look, now I have everything I need to build my compound. Now notice it says deduce a possible structure for the compound. So how would I put all 3 of those pieces together? I'll show you how I would do it. I would take my aromatic ring, I put the methyl group on it, and I put the hydroxyl on it. And there you go. That is C7H8O. I would grade that 100% correct. Now, if somebody else in the class said, well, hold on, I did it like this. I put it together like this. I put, my ring, and then I put my methyl group here, and I put my hydroxyl here. I would grade that correct as well. Okay? What if somebody else did it like this? Okay? If somebody else wrote that, I would grade that correct as well, because there's no way for us to tell which one of these isomers would be the correct one based off of the information that I've given you. There are ways to distinguish between them. Probably the best way to do that would be to use either carbon NMR spectroscopy or proton NMR spectroscopy, but that's another class, right? That's another day. That's chapter 15, and that's going to be later on this semester. Give me a thumbs up if you're like, wow, that's a lot of information, to kind of put together into this compound sandwich. But once you see it, hopefully it makes some sense to you. And you can see how, practice is really, really important in this chapter. Okay, good, great, awesome. Again, make sure you look through all of the practice problems that I have listed as suggested practice problems for this class before your quiz on Monday. Okay, well, with that in mind, I thought we would turn our attention and do another problem that involves IR. I think this one is not as tough as the last one, and I'm doing my best here to project as much as I can on the screen. All it says is you've got a bank of 5 different compounds here. You've got 5 spectra, okay? And then it says identify the compounds. So see if you can identify the compounds, match them up with the spectra. I'll label them. Are they labeled already? Oh, shoot, they are. And they're in a funky order. It says A is here, E is here. What kind of person labeled this? B is here, C is here, and I hope this is a D. Yeah, there we go. So I don't know if I copied and pasted these into the file in a funky order or what. But anyhow, I'm going to give you a second to look at these first 4 that you can see on the screen and see if you can match them up with these compounds here. And again, I forgot to point out that all of these are isomers. They all have the same molecular formula, right? So if we use the mass spectrum to determine the molecular formula, this is really demonstrating how you can use the IR to pick it apart. So I'll give you a few seconds, and you can use the names if you want. Let me give you a minute to think about it. I'll try to stop talking. Okay, instead of me, just putting my finger on one of these, A, B, C, or E, since D is missing on my slide right now, I'm just going to throw this out there to my students. Is there anybody that has an inkling about any of these? Just thinking, hey, I think I know, could identify one of them maybe?
Is B2-butanone?
Is B2-butanone? I think you have a good, a keen observation there. Absolutely. Because, what would you see in 2-butanone? Really? I mean, what would you see in 2-butanone? The only thing I would expect to see in there would be the sp3 hybridized carbon-hydrogen stretches, right? Sorry, you guys, I can't draw very straight lines, but there you go. What you see here, okay? And the only other thing you're going to see is a carbonyl stretch, right? And it's just huge. This is the carbonyl stretch for the ketone. Now, if you look at ketone on your handout, it says 1750. Now, this is not very big, but if you look at it, you'll see it's pretty darn close. You have 16, 17. Look, that looks to me like it's pretty darn close to 17, 15 reciprocal centimeters. So I don't know who got that one, but I'd say you're pretty darn good. Okay. Let me just go back here. Is there anything else anybody was able to notice about any of these or think they might have it? And they might not be, the most abundantly clear, but maybe one more. C. Okay, so somebody says C is cyclobutanol. Okay, so one thing I noticed is there's two alcohols. The problem is that I'm not showing both of them at the same time. Right, one of the alcohols is this, okay, is cyclobutanol, and the other alcohol has a double bond in it, so it's this here. Okay, so I'm sure that most of you were able to figure out, right? Jonathan wrote down C definitely has an alcohol, right? And I'm sure that if I was to show you D, you'd all say, yeah, D's an alcohol too. So we know that C and D are the two alcohols, right? We have the OH stretch here, and we have the oxygen hydrogen stretch here too. And if you want to write in alcohol, you know, just to help the reader know, okay? Then you can look for the carbon oxygen stretch of the alcohol, which comes out around 1,000 to 1,250. So if we zoom in on these, we see 1,000. So, you know, here's probably my carbon oxygen stretch. Same thing here. This is my carbon oxygen stretch. But if we want to differentiate between these two, could anybody tell me, you know, which one has the alkene in it, right? Because one of them is an alkene and one of them isn't. D. Yes, yes, there. I like the way you think, Byron. So what Byron is saying is he's saying, or what he's trying to say is that D has two absorbances or peaks that are associated with an sp2 hybridized carbon, and he's 100% correct. Right? If you go over to your sheet and you look at alkene, it's the second thing on there. It says that at above 3,000, it's usually around 3,100, you have a signal. Look, if this is, and I'm going to do my best here, so this is 3,000. Come on, pen. This is 3,000. This is 3,100. Looky, looky. What's that hiding right there? Hello. That is an sp2 hybridized carbon-hydrogen bond, right, from our alkene. And also, you notice there's a pretty big signal right here. If you look at the alkene, around 1630, you have weak. Well, it certainly isn't strong, is it? Let's look. We got 1,500, 1,600, 1,700. That looks like it's darn close enough to me. Right? This is close enough to 1630 that this is a carbon-carbon double bond stretch, okay, that comes from an alkene. There we go. So perfect, you guys. This is great. Okay. So my students were able to determine that D is, or sorry, somebody else said that this one. Where's my chat here? I lost you guys for a second. Okay. Who was it? Lauren. Lauren said that C is cyclobutanol, and she's 100% correct. Okay. And Byron and I think somebody else pieced this one together and said, well, this one's the alkene. Good. You're both correct. You're all correct. This is good. Going in the right direction. So look, if we go back here, we can do some of these by process of elimination, right? So we've gotten rid of this one, this one, this one. I want to show you one thing myself, you know, that I haven't really gone over yet and might not be as abundantly clear to you guys. And that is the aldehyde. Okay. If you go over to your sheet, hopefully you have it printed out. You notice that you have the carbonyl at 1725. If you look at A and you go 1,500, 1,600, 1,700, that looks to me like it's the carbonyl stretch, okay, of an aldehyde. Why? Because it's pretty darn close to 1725 reciprocal centimeters. But more than that, there's two other signals that are more, and I really mean it, they're more indicative of an aldehyde. Again, go back to your sheet and you'll see below the carbonyl, it says 2750, 2850, what's called aldehydic CH stretching. So the stretching that comes from this bond here gives you signals at 2750 and 2850. So not a range, it gives you two signals at those two values. If you come down here, here's 3,000. This is 29, this is 28, this is 27. So you can see that it's pretty damn close to 2750 and 2850. So these are the and we'll write it down properly, the aldehydic CH stretch. So that's the dead giveaway that A is the aldehyde. So then we could put the structure of the aldehyde on here like that. Right? Again, as I told you, and I'm sure you're all figuring this out, is that the more practice you get here, the more it crystallizes in your mind. And I see that Megan nailed the last one. She said this must be the ethyl vinyl ether. Right? If we go up to the structure of ethyl vinyl ether, what are we going to be looking for? We're going to be looking for an alkene carbon-carbon stretch. We're going to be looking for an sp2 hybridized carbon-hydrogen bond. We're going to be looking for a carbon-oxygen stretch from an ether. Let's go down and see if it fits the bill. First thing I would do is draw my line at 3,000. Okay, look at an alkene and see what it says. Greater than 3,000. It's usually around 3,100. This would be the sp2 hybridized carbon-hydrogen bond from your alkene. What else should you have? You should have a carbon-carbon double bond stretch at around 1630. Well, in this case, it just doesn't happen to be weak, right? Here's 16, here's 17. So this signal here actually represents the carbon-carbon double bond stretch from the alkene. Now, if you're like, well, Mr. Dion, on my sheet it says it's weak, and here it's really strong. That's probably due to the some kind of effect that the oxygen has on it. Since oxygen is so electronegative, it probably affects the dipole of the double bond. And again, we know that the stronger the dipole, the stronger the signal, right? We went over that in the first lecture this week. What else? If we look at ethyl vinyl ether, not only does it have an alkene, it's also got an ether. Let's go over to our sheet. Let's look at ether. It says here ether, somewhere between 1,300 and 1,000. So here's 1,000, here's 1,300. Look at that. Come on, that's huge. That must be the carbon-oxygen stretch from the ether. Okay? And so this would be ethyl vinyl ether. There you go. We figured out all of them. Okay? It took us a couple of seconds, but that's the kind of rationale we use. And also, there would be no way, and I really mean this, there would be no way for somebody to ace this quiz and stepping into it without having studied. Like, I'll just use the sheet and that's going to help me do it. No, because you have to train your eye to recognize things like the aldehyde, right? There's no aromatic in here, but I taught you today how to recognize an aromatic, 2 to 3 signals between 1600 and 1475, right? You've got to train yourself to see these things over and over and over. And it's just like anything in life, the more you look at it, the more you're going to be able to recognize what the heck is going on. Okay, well, let's, in the interest of time, I have lots of different problems, but I want to back all the way up to the top here. And I want to spend some time looking at mass spec problems for a second here, because we haven't done a ton of those. So I'm going to take it right back here, just a multiple choice question. You see how this should be a really easy thing for me to ask on your quiz. Sorry, I'm just looking around here. I'll give you a second to think about this one. I'll just throw it out there to my students. Question number 1, it says, which of the mass over charge values corresponds to the base peak in the mass spectrum? If anybody has an answer, just throw it up here in the chat or unmute your mic. Always interested to hear what my students have to say. Yeah, absolutely. Megan, Advita, yes. Lauren, you're all, yes. Kayla, you're all right. You're all correct, okay? Everybody's saying that it's C, okay? Remember, the base peak in a mass spectrum is the tallest peak, okay? Tallest peak, which we assigned a relative abundance of 100%. And since this is the tallest peak right here, what's the only logical answer? It's below 30 and it's greater than 20. So the only possibility is 29. Okay, let's move on to the next one. It says, which of the mass over charge values correspond to the molecular ion in the following mass spectrum? So now we're looking for the molecular ion. Anybody have an idea about this one? Yes, good. Okay, so Megan says it's B. You're absolutely correct. So the molecular ion, right, is our M plus ion, which is this one here, which is at a mass overcharge of 44. Well, you might be tempted, to say it's A, but remember, what is this little peak here? This is the M plus 1 ion, right? Which we get from the carbon-13 isotope, because carbon-13 is about 1% abundant. And so 44 would be our molecular ion, which is what's produced after we bombard the organic compound with high energy electrons. We knock an electron off, we make a radical cation. Okay, and again, the M+1 ion is going to be a very, very small peak, which is to the right of the molecular ion. Okay, the next ones, we'll go over them quickly. I'll see if my students can solve these quickly. Probably do it faster than I can. Again, you're allowed to bring in a calculator, a non-programmable calculator for your quiz. So no TI-84s and things that you can program the entire textbook into. We generally speaking frown on that. So if we do this first one here, we have our HDI. It's going to be equal to 1/2 times 2 times 14 plus 2 plus 2 nitrogens, subtract 14, subtract no halogens. So we have 28 plus 2 is 30, 32, 32, subtract 14 gives us 18. We divide that by 2, and we get an HDI, which is equal to 9. For the next one, we have C9H11N. Let's do that one. So we have HDI is equal to 1/2, 2 times 9 plus 2 plus 1 for the nitrogen, subtract 11, and there's no halogens. So we have 18, 19, 20, 21, subtract 11 gives us 10. 10 divided by 2, the HDI is equal to 5. Here we go. Again, I'm sure you guys are faster than me at that. Well, with that in mind, I'm going to give you guys a second to try to solve number 5. And if you have time, you could take a look at number 6. I'll give you a minute. It's hard for me to not be talking in class, but I'll give you a minute to try it. Number 5. Does anybody have an answer for number 5? Yeah, okay. Kayla says it's D. Let's give it the old college try. Again, what were the masses that we would use, okay? Because in this compound, we have how many carbons? We have 1, 2, 3, 4, 5, 6 carbons. How many hydrogens? We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and we have 1 oxygen. Now, what were the masses that we used? For carbon, we used 12. 12 times 6 gives us a mass of 72. For hydrogen, we use 1. Again, we round to the nearest AMU times 14, which gives me 14. And then for oxygen, we use 16. And we have 1 of those, which gives us 16. So you tally that all up, it's 30 plus 72, which gives you 102. And so that would correspond to the molecular ion for this compound. Another thing you could do with this problem is that you could eliminate E right away. Could anybody tell me why I could just look at the possible answers and get rid of E in an instant? What's the problem with E? And there's a big problem. Yeah, exactly. Is that E is an odd number, right? So odd number. And since there's no nitrogen in the molecule, it can't have an odd mass. Okay, well, you kind of solved number 6, didn't you? Okay. Number 6, which of the following compounds has an odd molecular ion? Who could tell me? Don't have to spend a lot of time on this one. Don't need a calculator. Yeah, thanks, Kayla. Thanks, you guys. Thanks, Advita. Exactly. It's B, right? It's number 2. Why? Because it's the only one with 1 nitrogen in it. So there you go. We just write down odd number of nitrogens in molecule. Right? C has nitrogens in it, but since we have 2 nitrogens, when we have 2 nitrogens, it means you're going to have an, can't write today, it means you're going to have an even mass. Okay, there we go. Let's move on. You guys are killing it this morning. Going really well. Next one, just tell me which one of these spectra has bromine in it. Out of these 4, who can tell me which one has bromine? And hopefully, if you have this printed out, it might be hard to see these mass spectra if you're looking at a little computer screen. But if you print it out, or if you have a PDF of your own on an iPad or a tablet, Byron, I don't think it's number 3. Why are you thinking? So what are we looking for when we have bromine in a compound? We have our molecular ion, right? And we have our M+2 peak, and they're in almost 1-to-1 ratio. Yeah. So the answer is what Lauren put. It's the first one, and Kayla, it's the first one. So if you look here, you see that we have these 2 peaks right here. So you have your molecular ion, and you have your M+2, and they're about 50-50, right? 1-to-1. If you look down here, right, you have these 2 peaks that are close, but they're nowhere near. They are not a 1-to-1 ratio, first of all, and also they're not the molecular ion, which looks like it's up here around 72. Okay, so this is your molecular ion. Okay, and it's definitely not the other 2. There's no M+2 peak for either of those. I mean, 1 is the only one with an M+2 peak in it, and so the answer would be the first one. All right. Well, there's some time left. Keep rocking and rolling with it here. Let me just try to pick another problem here. Let's take a look at this one. Which one will be consistent with the mass spectrum below? I think that I took this problem from, I've used it many times in this class. I think that I tried to enhance the line now that I look at it. So it goes 70, 71, 72. This here is 73. Okay, so with that in mind, I'll go back out here and I'll get my students to see if they can identify which one of these would be the best answer for number 8. Yeah, okay, good. I see a bunch of people putting D. Sorry, my computer blacked out here for a second, so let me fix it. There we go. Okay. Where are my students? There we go. Okay, I see that Byron and Josh both put D. And you're both right. Right? Why would it be D? How did everybody figure that out? It's not a trick question either. Mr. Dion does not like the trick. Byron, you're 100% correct. It's because the molecular ion is odd. So this is the molecular ion here, and it is odd. Now, if you're a real stickler and you're saying, Mr. Dion, where's the M+1 peak if it's got carbon? Well, it's probably in there, right? But you can see it just happens to be really, really small because this peak isn't the base peak. That's all, but it's there. Okay, so the molecular ion is odd. Therefore, nitrogen, we'll put here, odd number of nitrogen present Okay, and so the only possible answer would be D. I want to look at this one in a little more detail, right? If you draw out the structure of D, okay, here's the structure of D. Now, you remember what we talked about during last lecture. I said that if you take an amine, it can undergo what's called alpha fragmentation. So first you hit it with 70 electron volts. You make a radical cation. So you end up with something that looks like this. Okay? And then if this is the alpha carbon here, this is also an alpha carbon, but since it's symmetrical, we'll just draw one of them. You can break that bond between the alpha carbon and the beta carbon right here. So if we break that, we end up losing a methyl radical. Okay, so we'll put here, and again, you don't have to be able to draw the mechanism for this that's shown in our textbook because we haven't covered chapter 10. All you have to do is you have to understand that you have loss of a methyl radical. So that means you're going to have your molecular ion, right, and you will have lost 15. So if we take 73 and we subtract 15, okay, so get your calculator out if you need it, and you put in it 73 minus 15, and you end up with 58, okay? And then if you look over here on your spectrum, you see that we have a big old signal, or a peak here for mass over charge is equal to 58. So this is the loss of, do it like this. We'll draw it like this, and we'll say loss of the methyl radical by alpha cleavage. Okay. So again, the carbon that is next to the oxygen is the alpha carbon, and the next one is the beta, and the cleavage occurs between the alpha and the beta. Okay. Again, the mechanism is shown in the book. Never going to ask you to. I might ask you to draw after we've learned chapter 10, but that's later. I mean, we don't cover chapter 10 until April, so don't have to stress about it in February. There you go. All right, let's take a look at number 9. Okay, and we could sit here and talk about number 9 for the rest of the class. I'll try to make it quick. It says here, which one of the following compounds is consistent with the mass spectrum shown below? Okay, and notice that it says molecular ion not present. Now, what have we got down here? We've got A is an alkane, B is an alcohol, C is an ether, D is an amine, and E says none of these. Does anybody have the textbook open? Because if you do, I'd like you to go back to the section that deals with fragmentation of alcohols, what I covered in class last week. And let me read to you what it says if you don't have your textbook open. It says fragmentation of alcohols. First sentence, the mass spectrum of an alcohol will typically not exhibit a molecular ion peak because alcohols readily undergo fragmentation in a mass spectrometer. 2 fragmentation patterns are commonly observed for alcohols, alpha cleavage and dehydration. Okay, so what was the first thing I said in the first sentence? It said the mass spectrum of an alcohol will typically not exhibit a molecular ion peak. The only one of these that is an alcohol is B. You could literally solve the problem that quickly. Okay, you could say if there's no molecular ion, all the rest of them, the alkane, the ether, the amine, there's no reason why any of these would not produce a molecular ion. Okay, so that's the first, kind of thing that we can think about when we look at this problem. But we've got time, and I want to talk about this spectrum a little more just so that we understand what the heck is going on. So I want to analyze that compound. Okay, so this compound right here, that is 2-butanol, so I'll draw the structure the way it is here as a bond line structure. Okay, so that's B. That's the structure of the compound right here. The formula of this compound is C4H10O. So 4 times 12 is 48, plus 10 is 58. 58 and 16 give you 74. So we have 74, and that's where our molecular ion would be. The molecular ion would be at 74 if we could see it, but we can't see it. Now, what kind of fragmentation can the alcohol undergo? Generally, it's either going to undergo alpha cleavage and dehydration. Okay, so it'll undergo both. Now, if we take 74 and we do a loss of water, so I'll write it in blue because water is blue, right? Loss of H2O. And H2O weighs 18. We have 74 subtract 18. So 74 minus 18, and we end up with 56. Okay. Now I don't see a big peak at 56. You look, we got 55 amine, and 56 is pretty measly. So remember that not every alcohol in the world is going to do the same thing. They're not all going to lose water and give you a big peak. Some of them will, some of them won't. So I don't see a big peak for loss of water. So what I want to turn my attention to next is the alpha cleavage. And there's two ways that this molecule, two different ways that this molecule can undergo alpha cleavage. Let me prove it to you. Okay, I'll do it in green and I'll do it in, where's my pencil? I'll do it in green and I'll do it in red. So if this is an alpha carbon and this is a beta carbon right here, okay, we can get an alpha cleavage. Sorry, my mistake. This is our alpha carbon and this is a beta carbon and this is a beta carbon. So if we have alpha cleavage between the alpha carbon and the beta carbon, then we would lose loss of CH3, CH2, which is an ethyl radical. How much does an ethyl radical weigh? It would be the molecular ion subtract 29, because that's how much it weighs. And then you'd end up with this fragment here, okay? Again, I'm not going to ask you to draw the structure, but it's a resonance stabilized carbocation, and you guys all know what that is, right? So we would see M minus 29. If you take 74 and you subtract 29, let's do that. You take 74, subtract 29, and you end up with 45. Well, looky. I have the base peak is at 45, and that is due to loss of the ethyl radical, okay? Now, normally we don't write out loss of ethyl radical. I would just write loss of CH3, CH2 radical, okay? Or you could also say molecular ion subtract 29. Let's take a look at the other alpha cleavage. Here's my alpha, here's my beta. So if I do a cleavage here, then I'll have loss of a methyl radical. Remember, radicals are uncharged. They're not detected in the mass spectrum. So that would be the molecular ion subtract, how much does a methyl radical weigh? 12 plus 3 is 15. So if you take and you draw what you would end up with, you'd end up with this. Again, I'm not going to ask you to draw these because we haven't covered chapter 10. Anyhow, so we have 74 subtract 15. And when you take 74, subtract 15, you get 59. Well, looky. We have a peak here at loss of the methyl radical, okay, which is the molecular ion subtract 15, okay? So just by having the knowledge of what's in our textbook, and the write-up about alcohols isn't long, just by knowing that an alcohol doesn't give us a molecular ion, we were not only able to determine which one of the answers is correct, but we were also able to determine two of the major fragments, right? So there you go. Okay, give me a thumbs up if that clears up some, and you're like, yeah, I get it, but I'm going to need to practice, which is totally normal. Again, nobody gets out of this chapter without practicing. It'd be very, very difficult to master the content without practicing. Anybody with me? All right, thanks, Jessica. Great. Okay, so somebody says, how do you know what is an alpha carbon and what is a beta carbon? So without me going back into my slides, well, I guess I could. You go back in here, okay, and go way to the end of the chapter. We talk about alpha fragmentation, okay, alpha cleavage. So if you have an alcohol, okay, here's an alcohol. The carbon that the oxygen is attached to, that's the alpha carbon. When you have an amine, the carbon that the nitrogen is attached to is the alpha carbon. The carbons that follow the alpha carbon are the beta carbons. That's it. Cool? Does that help? Nothing more than that. All right. Good. No problem, Josh. Where was I? Oh, somewhere in here. How much time do we have? We have time. I wanted to look at another problem. Let me find it. By the way, the solutions to all these are posted to Canvas, so you can have these for your perusal. Anyhow, let's take we don't have a ton of time. Let's take a look at 10. Number 10. Could anybody identify, I'll throw this out there. Maybe I should ask some different questions. Could anybody identify the molecular ion, the mass of the molecular ion? And it's not a trick question, okay? Just looking at what you see here on the screen. What would be the molecular ion here? Its mass. Yeah, absolutely. It's 72. All right, this is our molecular ion right here. Okay, it's got a mass over charge that's equal to 72. Right, this is the M+1 ion. Okay, there we go. So there's our molecular ion. And then all it's asking us to do is, what's the question? Which one of the following compounds is consistent with this mass spectrum? I want you guys to look at the answers. And could anybody tell me, is there one of these answers I could get rid of immediately? Just be like, no, not happening. Yeah, thanks, Lauren. Absolutely. So the answer is not going to be B. Now, this one might take you a little more time, but again, you can bring in the cheapest calculator known to man, okay, for the quiz. All you need is like a 99-cent calculator, okay? And if you calculate the masses of all these, which I did really quickly, so here you have C5H12, which has a mass of 72. The next one is an alcohol. It has C4H10. Oh, didn't we do this just a second ago, which is 74. And the next one is an ether, but it has the same formula, C4H10, which is 74. So if you're wondering, like, Mr. Dion, is that all it is? All I have to do is tally up the masses, and that would be the right answer? Yeah, absolutely. That's it, man. That's all there is to it. Let's draw that compound and think about what might happen with that compound when it gets into a mass spectrometer. So that's this compound here, 2-methylbutane. Now, how is that going to fragment? Well, I mean, you could lose this methyl group, you could lose this methyl group, you could lose this ethyl group. But I'd say that the loss of the ethyl group would probably be the most common of all these. Maybe not, but maybe yeah. And why? Because it would produce the most stable carbocation and the most stable radical. So let's just take a look. If we had the molecular ion minus 29, so that would be 72 minus 29. That would give us 43. Let's go over to our mass spec. Let's see, we got 40, 41, 42, 43. Look at that. The base peak is at a mass over charge of 43. And again, the reason why I suggested that is because it gives you the ethyl radical, okay? And it would give you this carbocation, which is a secondary carbocation. If I was to fragment one of the methyl groups off, which is totally doable, and we're going to see that, that would be the molecular ion minus 15. And when I take 72 and I subtract 15 from it, I get 57. So that gives me 57. And the pieces that I would end up with would again be a secondary carbocation, which is going to be just as stable as that one. But what kind of radical do you get? You end up with a methyl radical, and a methyl radical is not as stable as this primary radical. I went over that during the last lecture. So do we have a peak at 57? And the answer is yeah, and it's big. Okay, look, if you have 55, 56, 57, there you have it, my friends. Mass over charge is equal to 57. So this is the kind of rationale you want to have when you're looking at mass spectra. We get time for one more. Give it the old college try here. It says, which one of the following compounds is consistent with this spectrum? I know you guys can solve this even faster than I can. I'll zoom in here. Who can tell me what the molecular ion is here? And it's not a trick. Not like trick questions. Yeah, thanks, Josh. Absolutely. The molecular ion is equal to 101, right? This is the M+1 peak here. So it's got an odd odd mass, therefore odd number of nitrogen. We look over here, the only possible answer would be B. Now you could draw that compound out. Look, it's educational, you guys. Look, you draw the compound out. Beautiful secondary amine. It's called dipropyl amine. Okay, there it is. Here's your alpha carbon. Here's your beta carbon. See what happens if you have alpha cleavage. You'd have a loss of 29. So if you take 101 and you subtract 29 from it, what do you get? 101 subtract 29. You get 72. Okay, again, this is the alpha cleavage. Okay, 72. Let's take a look here. 70, 71, hot diggity darn. We have a big old peak here. It's the molecular ion minus 29, which is the result of alpha cleavage. Okay, loss of the ethyl radical. There you go, my friends. Who's feeling a little more confident, after today? I hope you are, because we did quite a bit of practice. Saw some interesting things in the IR. We saw aromatic, right? We saw an aromatic ring. We know how to recognize that. We saw an aldehyde. We also looked at an ether, which we hadn't looked at before. We spent quite a bit of time talking about alpha cleavage and what that is. I think might have been somebody asked a really good question about Josh, asked about alpha cleavage. We cleared that up. Which was the alpha carbon, which was the beta carbon. We talked about fragmentation, radicals, right? Molecular ions, M+1 peaks. We talked about the isotope effect. Byron asked a question about which one was it, Byron? I can't remember. If I go back here, he asked me something about a chlorine. When you have a chlorine, so none of these mass spectra have a chlorine present in them, zilch, zero, none of these do. When you have a chlorine, you'll know it because you have exactly like your molecular ion. You have your molecular ion, which will look like this, and then your M+2 peak will be exactly a third of the height. Okay, your M+2 peak, and you don't see that in any of these. Okay, it's exactly going to be right on there. It's going to be a third. Okay. Where am I? Students. Where are my students at?